Hello, am I audible? So, hello everyone. So, as you guys know, that Stamatics is offering projects this summer. We have this session to give you all a brief introduction about each project. Let's start with eavesdropping 101. Are the respective mentors here?
Yes. Am I audible?
Yeah. Hello. Okay, so you can screen share and start your presentation.
Yeah. So I'll screen share. Okay.
Hello,
You'll have to
everyone.
give me permission.
As you guys know, that Stamatics is offering projects this summer. We have this session to give you all a brief introduction about
It
each
just
project.
says host disabled
start with
participants
eavesdropping
screen
101.
sharing.
Are the respective mentors here?
Where do I ask? Yes. Am I audible?
Yeah. Hello. Okay, so you can screen share and start your presentation.
Yeah. So I'll screen share. Okay.
Hello,
You'll have to
everyone.
give me permission.
As you guys
I
know that
cannot
ask
screen
for it.
share. It just says host.
We have
Okay,
this
I
session
cannot.
to give you all a brief introduction about
It
each
just
project.
says host disabled
start with
participants
eavesdropping
screen
101.
sharing.
Are the respective mentors here?
Where do I ask? Okay, so is the presentation visible? Can anyone confirm?
Okay, so yes. You can screen share and
Yeah.
start your presentation.
So hello everyone, I am Rahul Jha and me with Ravija and Devansh will be offering Eavesdropping 101. It is a project on cryptology and I would like to stress on the fact that it is a project on cryptology and not cryptography. So the difference is cryptology is cryptography plus script analysis, right? And most projects on cryptology they just focus on cryptography, so they focus on the implementation of algorithms and what goes on to like build those algorithms, for example the requisite number theory and stuff. Now we believe that is we do not believe in that approach because let's face it, none of us will ever have to implement the algorithm on our own, and that is because vetted verified implementations exist and they are open sourced. So this project will focus on how to find flaws in those algorithms and how to use those flaws to break them. So this project is going to be focused on crypt analysis rather than cryptography. So this is a very short PPT and we'll just be going over the basics. So our intended audience is Y22s. We intend to take around 30 of you. The prerequisites are basic mathematical maturity, and you should be familiar with any scripting language. That can be Python, that can be JavaScript, anything that you are comfortable with. And the screening test will be based on MCQs on probability and logic. And there will be an online task, a very easy online task that you will have to solve. Now, what can you expect from this project? So, we expect 5-6 hours of weekly commitment from you. And this project will involve a lot of maths, but most of it will be easy. Like think of basic probability theory. If there are 64 plausible options, out of which only 16 can occur, what is the probability? 1/4. There will be some set theory and some group theory involved. You will have to write a lot of code to solve the assignments, but you can do that in any language you are comfortable with. However, we would appreciate if you do it in Python. And here is a tentative timeline. So we expect that this project will take 8 weeks. We expect that this project will take 8 weeks. The first week, we will be introducing linear ciphers, cryptanalysis and stuff. In the second week, we will be introducing mathematical tools that you would need for this project. Weeks 3 and 4 will be focused on DES. Weeks 4 and 5 will be focused, week 5 and 6 will be focused on AES. And 7 and 8 will be focused on the modern crypto systems, hashing and applications. So this is the basic overview of the project. Now, if you have any questions, I'm open to them. We have some time. So does anyone have any questions? Okay, then I'll take that as a no. Thank you.
Thank you, Rahul. Okay, so let's move on to the next project. Some problems in combinatorics. Are the mentors present here?
Yeah.
Okay.
Yeah. Okay. So Yeah, so I may have made a slightly longer presentation than expected. So organizers, please stop me if I go over time. Yeah, so this project will be somewhat different from the way usually projects are done. So there is no sort of fixed topic that we will be going over, no textbook that we will be following, but the goal will be sort of to just try solving some interesting problems in combinatorics. So, and there is no fixed sub area of it. So anything that looks interesting, that is somewhat open, that something that I don't know how to solve and is interesting to whoever is involved in the project. So that is all fair game. So to give you some flavor of what kinds of problems I'm talking about, so here is, yeah, yeah. So here is one recent work of Defent and Kravitz where they introduced foot sorting for socks. So suppose you're given a bunch of unsorted socks in a line, okay, and you want to sort them. By sorting them, I mean you want to bring socks of the same color next to each other, and the only way you can do it is using your foot. What you can do is that you can take the first sock in the line of unsorted socks, put it on your foot, or you can remove the topmost sock on your foot and add it to the line of sorted socks. Okay, so for example, in this case, what you would do, you would put on this red sock, and you would come here, then you would maybe, sorry.
लेकिन तब थोड़ी गान में फटी पड़ी है.
Is there a question?
Sorry, please, everyone else, keep your mics muted.
Yeah, so you put on this red sock, you take it off and add it to the sorted pile. You put on this blue sock, and then you can put on this next red sock on top of the blue sock. You take off this red sock, so the red socks are together now. And okay, I may have skipped a step here. Yeah, so after taking off the red sock, you put on this blue sock, and then again, like going in this way, you will have sorted this set of this line of socks. Okay, so now the first question that should come to your mind is 1 foot always enough? Can you always sort a bunch of socks using just 1 foot? And the answer is no, it is not obvious. But so what Defent Kravitz, so they give a lower bound for like how many feet do you need to sort a bunch of socks with, say, n colors. Okay, but you can also ask the other way around. So is there will a finite number of feet always suffice? So of course you can use n feet, for example, to sort socks in n colors. But what they show is like a precise bound. So they show that every sock ordering with n colors is log n foot sortable. And there exists sock orderings with n colors that are not log n minus 1 foot sortable. So maybe I should define first what it means to have multiple feet. So suppose you have like 2-3 feet. So again, like the idea is the same. You can either take the first unsorted sock, put it on the leftmost foot, means the first foot, or you can take off a sock from 1 foot, put it onto the next foot, or you can remove a sock from the last foot and add it to the sorted line. So this is what it means to sort with multiple feet. So one question they ask is, okay, so we know that log n minus feet don't suffice always for n colors, but how big is this sock ordering? So what is the number of socks that you need in each color class for this case? So they don't even know whether this number should be unbounded. Okay, so maybe like some constant number suffices. So this is one question they ask. Another question is, well, suppose you did know that each color class has exactly 2 elements. Okay, so like a normal, like you have distinct normal pairs of socks. Okay, then how many feet do you need? So of course the upper bound from before continues to hold, and the lower bound they have is off by a constant. So it's like a quarter of this thing. So again, the natural question is to improve these bounds. So this is one kind of problem that could potentially be looked at. It's not the only kind. So here is another problem that might be interesting. So this is a Ramsey problem on daisies. It is inspired by a problem in query complexity that was of interest to me. So what is a daisy? A daisy is a special kind of hypergraph. So a hypergraph is just, so you have a bunch of vertices, which you can think of as the universe of your set system. You have a bunch of edges, which you just think of as a collection of sets. These sets are uniform in the sense that they all have the same cardinality. So in this case, V is going to be of size k plus m, which you can think of as the numbers 1 up to k plus m. And each edge in E is going to have size exactly k plus r. Moreover, these edges will be of a special form. So each edge will contain the numbers 1 up to k in it. So you have this core which is common to all the edges. And what you do is that out of the remaining m points in the universe, you take any r of them and add it to this set. Okay, so this is a very special kind of hypergraph. And so here's an example of what a 1, 4, 2 daisy might look like. So 2 is the size of the core, which you see in the center here. 4 is the number of points outside the core, and 1 is the additional point you will add to take in each edge. So this is an example. So now here is the problem that I'm interested in. So let DH denote the smallest k such that if you take this hypergraph where you have these 2 into k plus h many vertices, and your edges are basically, you include exactly half of those vertices in each edge. Okay, so it's the complete k plus h uniform hypergraph that you get on 2k plus 2h many vertices. And now you color each of these edges with some color, red or blue. So now the question is that you would want k to be large enough so that it contains a monochromatic H2HK daisy. So now I know the parameters can be annoying, so like it may not be easy to remember in such a short time, but remember that k is the core that we want, 2h is the points outside the core, and h is how many points from outside you will add in each edge. Okay, so since we have 2k plus 2h many vertices totally, what you're saying is there are k vertices which will be present in each edge, there are k vertices which will be present in no edge, and out of the remaining 2h vertices, you add in all possible ways h of them. Okay, and here are the what we know about them. So like some very basic bounds. So it can be shown, again, these are not trivial, of course, that dh is upper bounded by the Ramsey number for h uniform graphs for for the Ramsey number for h graphs for the number 2h and minus 2h. So this does not matter really, but this is a very quickly growing function. So this is like a tower of 2's of height h. On the other hand, the lower bound is just doubly exponential in h. The question is, can we improve these bounds? And so the lower bound is especially of interest to me, but even the upper bound would be very interesting. Yeah, so on to more boring stuff. So here are the logistics for the project. So this is also available on the website. So that's why.
Hello.
Is there a question?
I don't think so. Farzan, you can continue.
Yeah. So I was saying that, so this stuff is available on the website also. And maybe I'll just make a few disclaimers. So this is a completely useless project. It is not going to help you get a corporate job in any way. It will be somewhat weird if in an interview you say, I spent my summer counting directed animals and certain special kinds of forests. But yeah, do it if you're really interested in it. On a more serious note, so I haven't done such a thing before, and maybe my taste is not so good for a general combinatorics audience, and maybe I don't have enough experience in figuring out what problems are actually accessible. But still, I think this will be a very interesting learning experience for all of the people involved in the project. And finally, I would just want to say that you are, of course, welcome to bring your own problems, whatever kind of stuff you are interested in. You want to count things, you want to look for bijections between new classes of combinatorial objects, you want to do some kind of Ramsey business, you want to solve some Turan problems, some graph theory, or you want to work with like some discrete geometry or anything which has something to do with combinatorics. Of course, for many of these things, I know very, very little, but we can still learn and figure out things as we go along. Yeah, maybe I've overshot my time. Yeah, if there are any questions or maybe they want, I don't know, organizers, is there time for questions?
We'll take the question.
I want to ask that while we were preparing for JEE, the level of combinatorics we studied, is that enough? Or we need to have some basics? After that, we can start solving the projects.
Yeah, I mean, you can get in touch with me to know more maybe, but so basically, I would say something like a basic course which is done here is like CS201. So you can ask people who've done that course, or look at a basic book in combinatorics, something like maybe Miklos Bona has a book called A Walk Through Combinatorics. So some things from there would be useful. So something beyond JEE would be useful. But even if, so you should just get in touch to know more maybe. Anyway, so anybody who wants to do this should get in touch anyway. so that I'm aware of your background and like we can look for problems suitably. So this will be, yes, it's not going to be a uniform project that everyone is doing the same thing. Okay, so maybe we'll like split into pairs or like small groups who are focusing on a single problem or something like that. Okay, so it will be quite different, I suppose, from other projects.
Thank you, Farzan. We'll take the rest of the questions at the end of the session.
Sure.
Okay, so let's start with the next project, an introduction to geometric deep learning. Are the mentors present here?
Yeah. Is my screen visible?
Yes, yes.
Okay, great. So this is project number 3, geometric deep learning. Here we will be talking, or rather giving you a brief introduction to the concept of geometric deep learning. So why am I squeezing the word geometric here? So machine learning happens to be a very broad term. And like, even if you don't know a lot about it, you would have already heard a lot of buzzwords being thrown around: CNNs, GNNs, adversarial networks, large language models. And well, machine learning encompasses pretty much everything under this huge basket of things. But is this kind of differentiation really necessary? Unification is what we actually want. And it has been shown in a lot of fields that when we try to unify things and get rid of unnecessary complications, we are able to find much more beautiful discoveries. So whether that is for the case of the grand unified theory of physics, or there is the constant complaint that chemistry may rules have too many exceptions, or whether that is the ZFC in mathematics. But everywhere, all around the world, scientists are always trying to find things that can make their give a brief set of rules to explain a large set of concepts. And geometric deep learning is exactly that theory for machine learning. And this is why it's often called the Erlangen program of machine learning, because the Erlangen program is what finally unified geometries such as Euclidean and other spherical geometries into one one simple set of concepts. And geometric deep learning, we will be studying the things that will help us to remove away all these complications and arrive at a single set of rules for this machine learning framework. So a random quote just to pass the time. And we'll move on to what we'll be covering. Meher, if you could take over.
So we'll cover the following topics.
Was there a question?
Sorry? Okay, so
no, I thought somebody was asking.
Okay. So in this project, we'll first start with how ML is done today and what geometric deep learning has to offer. After convincing you about geometric deep learning, we'll start working with graphs. We'll teach you the framework and then we'll start solving problems. Then we'll teach you about heterogeneous graphs and knowledge bases, and then move on to geometrical neural networks for recommender and other cool things. So the logistics of this project are as follows. First of all, the only prereq is proficiency in Python programming. Having ML experience will be helpful, but it is not necessary in any way. This project will be about 8 to 10 weeks long, and you'll be expected to commit 6 to 8 hours per week. And we will have bi-weekly assignments in this project, and they'll be done on Google Colab. So expanding further on the prereqs, Python programming will be very important. You should be comfortable with at least writing classes in Python. ML is not necessary, but it will make this project easier for you, especially in the first few weeks. Math, similarly to ML concepts, is not necessary. It will help you out, but you can easily learn it along the way. So thank you, and please don't hesitate to reach out to us on the following Discord IDs.
अरे भाई तू एकदम बाल.
I'm sorry, please mute yourself. This kind of behavior will not be tolerated. Thank you, Meher and Aniruddh, for the project. I think we can move on to the next presentation. So let's move on to the next project. Build your own computer vision library. Are the mentors present here?
Yeah.
You can share your presentation and start with the project.
Just a minute. I'm having some problem. Hi, hello. I'm audible?
Yes, yes.
Yeah. Is my screen visible?
Yes, Pratham, it's visible.
Okay. So hi everyone. So this project is going to be on building a computer vision library in the language which we all are familiar with, which is C. So first of all, hi. So you would have heard of machine learning libraries like PyTorch and TensorFlow, which makes the life of machine learning engineers. So basically, these are libraries that are used very often in machine learning. So we are going to build such a library for computer vision. We will implement basic features, and this will be completely in C, right? Which you must have learned in ESC 101 or any other DSA course or something like that. So let's just skip this part. Okay. Okay, so what are we going to do in this project? So the first thing which we're going to do is play with sizes and pixels. So let's suppose we have to resize this part of an image. So we are going to, if you see the left part and the right part, right? The left part is just zooming into the picture, but the right part is a smoothed out picture. How do we do this? So we're going to learn how to do this in C. We'll play with colors, where we'll do grayscale, saturation. We'll change the saturation. You can see the animation here. We'll learn how to do this in C. Then you will be able to change the hue. We learn how to find edges. Like this is basically a line drawing of this picture, right? So how do we do this? We learn how to do this in C, and this will be a pretty math intensive, but it will not be anything apart from what you already know. So I think it'll be fun to learn this. We'll learn oriented gradients. And this is the last part of the project which we'll do, which is called panorama stitching. Suppose we have 3 images, right? And these are 3 images taken from the same point at different angles. And we need a panorama of these images. So we learn how to stitch these 3 into this, right? This is what we're going to learn in the last part of the project. And all of this will be written in C, right? Okay, so the prerequisites, first is programming in C. And even if you haven't done programming in C, you can complete up to the mid-sem syllabus of the course ESC 101 or 111, which is taken right now. And even if you aren't familiar with this or you don't want to do this, you can still join us, because learning C is not a hard thing, and you can learn along with the topic. So that's it, and we are going to build this library, and the expected commitment will be 4 to 5 hours from the mentees. And I think we are going to take as many of you as possible. So please do apply if you want to learn this. And these are the mentors and their contacts. If you need any more information on how do we build this, or if you want an example of the library which we have, I have the hosted GitHub. So you can ask me for it. Thank you.
Thank you, mentors, for the presentation. Let's move on to the next project. Introduction to measure theory.
Yeah, I'll be presenting just a minute.
Okay, thank you.
So I assume my screen is visible. So hi everyone, I'm Suyash, and I'll be offering a project which introduces measure theory and integration theory. I'm sorry that on the website it's not included the integration theory part, but I'll make the changes real soon. So moving on to the project description. Well, I can write up real sophisticated English words and English language and make, yeah. So and make the project seem quite difficult to understand and less insightful, but it's actually quite straightforward. It actually defines how we and defines how we measure sets. So basically, when given an open interval, we know what the length of the interval is. It's basically the supremum of that interval subtracted by the infimum of that interval. So, in itself, it doesn't seem that there is any discrepancy in defining it that way. However, when we move to the integration part, that in that place, in that topic, we understand that there is some vagueness in on the type of functions which are integrable. So basically, when we are integrating a function, Riemann integrating a function, we see that the function is allowed to have discontinuities on a finite number of sets. But actually, we have seen through examples that the number of points need not be finite, it can be infinite. However, that can be achieved if and only if we define the measure in a certain way, the length of an interval in a certain way. Also, we see that during Riemann integration, which we all have been studying for past 4 or 5 years, it's actually we have been dividing the domain of the functions, the Riemann sum. I'm talking about the Riemann sum. We divide the domain of the function and make the domain as small as possible. Sorry, make the partitions as small as possible to approximate the area under the curve. Actually, when we define this new way of measuring sets, we do not divide the domain. Instead, we divide the range of the functions. As trivial as it seems, it actually gives a pathway to a lot of things which has its application now in probability theory, function analysis, operator theory, etc. So as I've mentioned here, it gets convenient to have its concept clear before studying any of these topics. Right. So I'll move on to the logistics. So the prerequisite is actually just attempting the real analysis course, which is the MTS 301. I'm not asking for any kind of proficiency, and I will not be asking your grade in that course. I just want you to know what topics are there in real analysis, and then we'll go through those topics in the first or second week, whatever topics are necessary in the course. So yeah, this is the week-wise plan. The first week will be motivation and just reading till MTS 301 concepts. I'll be following the Stein Sakarchi book for real analysis. Then from week 2 to week 7, we'll start the actual project wherein I'll later mention that you will be presenting your stuff to the whole group, or by reading the specific portions which interest you. So we'll start with the definition of exterior measure, then move on to what measurability is. We'll then define measurable functions, then certain theorems which are necessary and very, very interesting. Then we move on to how we define integration of certain functions, which are quite, as the name suggests, it is simple. The functions are simple and the definition would be simpler than even the definitions of the function. The definition of integration of sophisticated functions, and then we'll move on to the L1 space of integrable function. Now this is the most important topic of all, because this will have its application in every single math topic which you will be if you will be pursuing later in your career. So yeah, my teaching methodology will be, as I mentioned before, that the mentees will be presenting the set topics in the previous week. That means not on the first week. From week 2, you will start your presentations. Well, this presentation, as I have learned in my experience, gives a lot of a lot boost to your soft skills and makes you helps you understand the topic much better. The presentations will include flowcharts along with proofs, not the straightforward, just reading out the stuff. You will have to make flowcharts and make us give us insights from whatever you have understood from the topic you are presenting. And obviously, the projects will be done on LaTeX. So if you are interested, because in pursuing mathematics, you have to have this skill of writing LaTeX quite proficiently. So yeah, this actually also enhances your later writing skills as well. Yeah, so weekly commitment, the duration will be of 8 weeks, I presume, and the weekly commitment will be of 6, 7 to 8 hours. Now, please note that this is the weekly commitment and not the daily commitment, because when I was in my first year, I got a bit confused, like what kind of a project offers asks for 8 or 7 hours for daily. So yeah, I'll just mentioning it here that this is the weekly commitment. And yeah, I think that ends my presentation. If you have any queries or questions, you may ask. So I'll take that as a no, and thank you.
Thank you, Suyash, for the presentation. We'll move on to the next project, Rubik's Cube meets group theory and algorithmic adventure.
So, hello, am I audible?
Yes, I.
Okay. So, for this project, can you go to the next slide? So, as a brief introduction for this project, we're going to use a tool out of abstract algebra called group theory to try to dissect and analyze the Rubik's Cube. And for this, we're going to split the project into two halves. In the first half, we're going to solely focus on group theory, where we're going to focus on different topics, different theorems that are important and core to group theory, and try to understand it thoroughly so that we can apply it on the Rubik's Cube. Over to you, Tarun.
And then we are going to use the concepts that we have just learned about group theory, and we are going to solve Rubik's Cube. We are going to be solving 3x3 Rubik's Cube in this project, but we can definitely extend our knowledge about the Rubik's Cube to 4x4 or 5x5 or other Rubik's Cubes. So we already have a lot of algorithms present on YouTube, and the algorithms, if we follow them, they definitely give us a solved Rubik's Cube at the end of that. But this project, the aim of this project is to build your own algorithms and to understand what is actually the mathematics going on behind them.
Yeah, so coming to the prerequisites and eligibility, there is no prereqs as such. I'm pretty sure high school mathematics is more than sufficient. Whatever you have done in JEE is more than enough. And coming to eligibility, everyone is eligible. Of course, there's no N2 is the key. Y22s are more than encouraged to take up this project, since this is a much more mathematically oriented topic than most people are like exposed to, and it would kind of improve mathematical thinking. And coming to the number of people we're expecting around 30 to 40. And if we have more than that many applications, we'll have a screening test. Now coming to the timeline for the project, week 1 would be basic definitions. We're going to focus on basic definitions of groups, basic properties that are central to group theory. We're going to focus on examples like the dihedral group, the symmetric group, etc. Focus on subgroups, examples of subgroups, etc. like that. Week 2 will be focusing on the Lagrange theorem, which is kind of like the ABCs of group theory, a very important theory for group theory. We're going to focus on other important topics like cyclic groups, order of groups, cardinality of groups, generators and partitions, etc. like that. And week 3 is the most important week, where we'll be focusing on some of the most important topics that would be required. We'll be delving into homomorphisms and isomorphisms. And for this project, the most important topic would be permutation group and the symmetric group. Given time, we'll also focus on group actions and stuff like that, which would be useful as well. Then after that, we would have our midterm evaluation, which will just cover all the topics we've covered in the first 3 weeks. Not hard. If you've understood everything, it should be fine. Over to you, Thal.
Hello. In week 4, we'll be figuring out different kind of configurations of the cube, rotations, front rotation, back rotation, right rotation, and we'll be giving them notations. And then we are going to create the main topic, which is the Rubik's group. In the Rubik's group, we'll be first of all proving that the configurations, the different kind of actions that we have studied they do form a group. In week 5, we'll be filtering out the configurations as valid or invalid by their existence, because some configurations that we have figured out, if we couple them together, they might not even give a configuration that is actually valid in the real world. We'll analyze the positions and orientation, and we'll find out a few 8 tuples and 12 tuples of the configurations, and those tuples will help us solve the Rubik's Cube. In week 6, we'll be finally figuring out the algorithms that are going to be used to solve the 3x3 Rubik's Cube. We'll start solving the Rubik's Cube with solving the top layer, then going to the middle layer, and then ultimately solving the bottom layer. Mention that this algorithm will work on 3x3 cube, but the notations and the configuration that we have already studied in the project, they can be extended to 4x4 and other Rubik's Cubes. So that is going to be very helpful. After this, we'll have a runtime evaluation where again we'll be summarizing whatever we have studied during this project. Thank you. We have the weekly commitment of around 6. The project will go on for about 6 to 8 weeks. We are expecting the participants should be willing to give around 5 to 6 hours per week. This can vary. The project duration, 6 to 8 weeks, can also vary depending on the circumstances. Thank you.
If you do have any doubts, please ask them at the end or drop a message at the Discord. Thank you.
Okay, so now we'll move on to the next project. Math data, empowering data science with mathematical tools. Are the mentors present here?
Yeah, we are here.
Oh.
So, hello, I'm Dishan Jain, and am I audible?
Yes, Dishan.
Yeah. So, project name is Math Data, empowering data science with mathematical tools. So, it's clear from our name that this project is going to be associated with data science. Okay, so this is our overview. Okay, so this project will aim to introduce you to the basic mathematics behind the data science and machine learning. In this project, we are going to cover various topics like basic probability and statistics. After this, we will go to linear algebra. We'll cover Python and its interesting libraries, which will be using in the data science and machine learning. After this, we are going to learn some algorithms related to machine learning, which is used for machine learning. And we are going to take weekly tests. And after this, at the end of this project, we are going to have a project to test all this knowledge. So this is after this, what is like the project objective, what you're going to learn from this project. So we will dive into the various forms and structures of information that you get, like how the information is represented in various forms. You will discover how to get insights and patterns, which will help you to make better predictions and decisions. After this, you will also learn like you have sometimes bad data and you will have to clean it, wrangle it, and process it before using it with algorithms and techniques to like predict and make decisions. Okay, so this is our objective. Now we will see how we are going to implement all the amazing things said by my co-mentor. In the first week, we will be learning Intro to Statics and Probability, where we will teach you basic probability stuff that will be used very intensively in the algorithms part when we will build algorithms in the further weeks. And in the second week, we will be using Python as our language. So we will be giving you some resources in the week 1 itself. So in week 2, when this is the time to learn Python, so we will be not focusing only on the theoretical knowledge which you gain. We will be giving you a code forces contest or any other similar platform where you would be implementing your knowledge in Python. And similarly, in week 3 and week 4 as well, we will be learning some libraries like NumPy, Pandas, Scikit-learn, and Matplotlib. And that will be also not a thorough reading of stuff. We will be giving you various examples and assignments through which you can solve and learn everything, and you can get your hands pretty dirty in the assignments, which you have to submit for evaluation purposes. In the week 5 and week 6 of the project, we will be learning much more interesting algorithms where you will be using these libraries and the statics and probability theory, which you have learned in the previous weeks. And we will be doing the math behind linear regression, logistic regression, and deep diving into the decision trees and random forests and how they work exactly. And in the 7th week, we will be just shifting our focus from machine learning models to time series analysis. And we will just tell you the difference between what is the exact difference between interpolation, extrapolation, and prediction, which we have been doing in the past few weeks. So this would be a different part. So you can just get a brief on it as well. And at the last of this project, we will be wrapping up by making a real life project. You guys, we will give you some topics where you guys can choose what model you have to make that can bring a significant change through what you have learned till now. So that will be a real life project which we'll be doing at the end of the project. So there are no such prerequisites for this project. We just require N2. N2 is everything. Now, and other than that, there is no theoretical prerequisite as well. Python programming is preferred if you know, but we will be giving you the resources beforehand when you get the project allocated. So you can learn in the first 2 weeks and give the contest and improve your Python programming skills. And everything will be taught from probability and statistics to Python programming and libraries. And we require active participation from all the mentees. No freeloaders will be entertained. You will be ratified based on 2 criteria. First is your assignments that you submit each week. And second is the participation you give in the offline meets or online meets we conduct to solve your doubts, etc. So 30% weightage will be given to that. We will more prefer Y22 because it's an introductory course to data science that will help you to build the foundation and learn the big world of data. So here are your mentors. My name is Dansigai.
My name is Deshan Jain, and feel free to reach us if you have any questions.
So that's the end of the presentation. Do you guys have any questions?
Mentors will take the questions at the end of the session.
Okay.
Yeah, kindly. Thank you, mentors, for the presentation. We'll move on to the next project, formal logic and automata theory. Also, a note to the mentors, we are kindly running short on time. So if it's possible, then please keep your presentations concise. Thank you. Are the mentors for formal logic presenting? Okay, cool.
Yeah. So hello everyone. We are the mentors for the project of formal logic and automata theory, and the mentors for the project are Abir, Rajwangshi, Bhavat, me, and Dhruv Garg. So for the project, we are mainly going to cover propositional logic and automata theory. So in this project, we'll explore 2 major pillars of mathematics and computer science, formal logic and automata theory. We are going to cover the basics of propositional logic, first order logic, and then in the end of the project, we are going to shift our focus to automata theory, which is a study of abstract machines that perform computations on inputs. It provides a basic framework for understanding the behavior of limitations of computer devices, and it has further use in computer science in the later stages. So coming to the contents. Next. In week 1, we are going to cover basic syntax of propositional logic, valuations as a function for set of propositions, meaning of various logical connectors, and validity and satisfiability and tautologies. Coming to week 2, we are going to cover a definition of a proof system, basics of natural deduction, various axioms of natural deduction, derived rules in natural deduction, and proofs in natural deduction. In week 3 and 4 of the project, we are going to see how mathematical induction is used for proving statements and semantics. Then we are going to cover 2 major topics, soundness and completeness in natural deduction. Then we are going to have assignments on SAT solvers. We are going to build a SAT solver on C++ and axiomization and its soundness and completeness. So over to Dhruv Garg for
So in week 5, we will shift our focus to the order language. We will cover the basics of the first order language and some definitions and semantics and the basics of the model logic. And going to the next week, just a minute, there is some glitch. I am unable to go over to the next slide.
Yes.
Sorry for the glitch. So coming to the week 6, we will cover the formal definition of finite automata, and generally we will be covering the concept of automata theory in this week 6 or 7, and it will be really interesting if you are joining this project and you are able to stay till the end. Then this is the thing, like you will find it very fascinating. Then coming to the methodology, the reading materials will be provided at the start of each week so that you don't find any problem. We will also ask you to submit a rough write-up on a few definitions and concepts at the end of each week. And there will be assignments which will consist of around 6 to 7 problems, and you will be asked to solve them on bi-weekly basis. And here are some reference books which you can also see for your help. We have written them here: Logic in CS and Theory of Computation by Michael Zipser. Then coming over to evaluation criteria, we will hold a midterm test and an end term test. And the performance of mentees in these tests will the main criteria for ratification. And both of these tests are must for you to attend. And the assignments which I told you just at the last slide, those will also be considered in the evaluation criteria. And this is the project which will also help for the computer science students in the next semester, that is Sem 3 CS 202 course. And it will be really helpful if you do this project nicely, and it will really help you in that upcoming. So that's all from our side. Thank you.
Thank you, mentors, for the presentation. Let's move on to the next project, from the discrete to the continuous and back. Are the mentors present here?
Yeah, hi, I'm just sharing my screen.
Okay, thank you.
Just a second. Okay, I hope you can see this. So this project is called From the Discrete to the Continuous and Back. The two main areas of math combinatoric studies the discrete, something that you can count. On the other hand, topology studies the continuous. So you can study things like surfaces with topology. I realize that a lot of you might not be familiar with what exactly topology is. So maybe you have seen a picture like this, which shows that a mug is topologically equivalent to a donut. So to a topologist, both of these are the same object, even though they look pretty different. So you can think of topology. This is not an accurate description, but you can think of topology as studying geometry, but forgetting the distance function between points. Of course, there are generalizations where you're not in Euclidean space, and therefore the distance function doesn't really mean much. But yes, that is roughly what topology studies. Now, although we will be doing some topology in this, we will be studying topology in this project, I would not require a lot of prerequisites, because I know that all of you have done MTH 101, where you have learned the definition of a continuous function and so on. And once you know that, you can easily generalize to abstract spaces. Right. So we are going to be covering which studies
Hello. Yes, Nubha was experiencing some net issues. Move it on to the next project.
Yeah. So let's. Okay.
I think this is the next. I mean, can I begin?
Yes, Rohan.
Okay. Right. So our project will introduce mentees to theoretical computer science, like basic concepts and terminology that comes up everywhere. So there are no explicit prerequisites, no criteria. We will be admitting mentees on a case-by-case basis. We'll reach out to them and discuss their background, interest in those things. We expect most of it to be online, except the part in April and maybe a bit of May. And it will be a reading group. Right. So we will present the topics that we have listed in the next slide. But again, it will be great if some of the mentees volunteer to present them. Mentees can also present topics of their own choosing at the end of the project. And the evaluation will be on the basis of involvement. By that, I mean, again, presenting and also being mentally involved in the presentations. The weekly commitment is that we don't expect a lot of time from mentees because, well, we are doing just some concepts. The duration is expected. I mean, 8 weeks is a rough estimate. It might go on for longer than that. So we'll begin with algebra. There is really no other way. We'll be doing basic structures, groups, rings, and fields because, I mean, they come up in a lot of places. Then we'll move on to the theory of computation. We will begin with simple models of computation, that is finite state machines and circuits. We might do another model if mentees want to, but through these we will illustrate sequential logic and combinational logic. In the next part, we will move on to Turing machines. We will, I mean, for those who don't know, Turing machines are like, it is like the big machine that describes any other machine and any algorithm. So through this, we will do the variants of Turing machines and compare them. And through Turing machines, we will also illustrate the limitations of sequential and combinational logic. Those of you who have I suppose some Y22s will find the lower bound thing, like they might be confusing what I just said with that. Lower bounds are difficult to prove for Turing machines. We'll be covering, we'll be discussing these things. Yeah, but by that time, we won't be doing the lower bounds that people talk about. We'll just discuss why sequential logic is, inherently handicapped. In the next part, we will do non-determinism and measures of complexity. Again, these two basically don't hold for, primitive machines like FSMs. Oh, by the way, FSMs are also DFAs, NFAs. They're all the same thing, and also sequential logic. So complexity measures are all trivial for those things in circuits. We will do them for Turing machines. By the way, this is the most important part. By this, I mean, this is what helps you the most when you're actually, doing computer science at beginning, rather than doing. In the weeks after that, we will let mentees present what they want. Some suggestions are here. Another one could be information theory. So, they can present, anything that we approve of, anything that is sufficiently related. Our plan here is that mentees begin reading theoretical computer science by themselves. This is not supposed to be a primer. This is supposed to be, we will try to prime you, but it is not an introduction in the classical sense. We will make the mentees read chapters from advanced books, during the project, and also papers that are accessible to them. Because these things I have seen them they took me a long way in, in theoretical computer science. Here are our contact details. Please reach out. Please, even if this is your third preference, even if you want to confirm that this isn't the right thing for you, I strongly suggest you reach out because, I can't explain all the nuances in this presentation. I think that is all. Are there any questions? I'm sorry, you're not taking questions, right? That is all from us.
Okay, thank you, mentors. We'll be moving on to the next project, probabilistic thinking. Are the respective mentors present here?
Yes, I'll be presenting.
Okay, thank you.
So hi everyone, I am Kumar Saurav, and today I'll be talking to you about my Stamatics project, probabilistic thinking. So the intent behind this project So the intent behind this project is to give you a rigorous backing in probability theory and therein equip you with the tools to make sense of a variety of diverse fields that you might explore in your stay at IIT Kanpur and beyond. So what we'd like to cover in this project is as follows. The first week, we would like to go over the axiomatic approach to probability. So we'll go through the formal notions of conditional probability, random variables, expected values, and some basic counting, some combinatoric tools such as generating functions, etc. Then the following 2 weeks, we'll look at a very interesting example of dynamical systems called stochastic processes, and we'll be dealing mainly with discrete time Markov chains. So we'll look at the limiting probability distributions of such chains, which is roughly the probabilities that you end up in certain states. And we'll look at some classical problems in these fields, such as random walks, the gambler's ruin problems, etc. We'll also look at some elementary examples of how to simulate these distributions using Monte Carlo methods. So how to use computers to generate these probability values, essentially. The next 2 weeks deal with probabilistic machine learning. So here we'll be looking at the Bayesian approach to machine learning, which is essentially how to use Bayes' theorem to iteratively update your models. So as you get new data, you update your models based on the feasible space that you now have. We'll look at the probabilistic classification problem in particular and a few tools to help us solve this problem. In the 6th and 7th weeks, we'll look at how to use random bits in algorithmic design. We'll learn some tools that will help us in the analysis of such algorithms. And we'll find that there is a rich, discrete probabilistic structure to the way that some of these algorithms play out. We'll also look at some very interesting results involving random walks on graphs and the probabilistic method, which is a very interesting tool that helps us prove the existence of certain mathematical objects without actually being able to see them or characterize them. The 8th and last week will be a gap week where we may add supplements as per the group's interest, and we'll provide you with time to finish up on your assignments. So the time commitment is about 6 to 9 hours a week. This may vary. For example, if you have done a course like MSO 201 or the CSE course on probability, you might not need to spend a lot of time in the first week. But yeah, we'll expect the time commitment to be in this range. We'd like to mentor a group of about 20 to 25 people. This project will involve assignments. They will alternate between theory assignments where we'll ask you to solve some problems or write some theory, and alternately we'll give you some simulation assignments which will involve writing programs to find the probability of something or to do something algorithmically in the case of randomized algorithms or ML. The assignments will have to be done in groups of 2, and the final assessment for ratification will be done via oral presentation. Yeah, that's all from me.
Thank you so much. Next up, we have from the discrete to the continuous and back. Are the respective mentors present here?
Yeah, I'm right here. Yeah, I was presenting this before, but my laptop hanged. I'm really sorry about that. But I was just talking about what topology is, because the 2 topics of study in this project are going to be combinatorics and topology. Right. So now combinatoric studies what is discrete, and topology studies what is continuous. And these 2 things seem like they are like duals of each other. Not duals, but they are completely complementary. But interestingly, a problem can be translated from one domain to the other, and they both enrich each other. So for example, on the bottom left, you can see what is called a triangulation of a torus, or what is called a donut. And when you triangulate a surface, you can extract a lot of information about it. For example, its homology groups, how many holes it has, and things like that. And pretty much most of the useful information about a surface you can extract from dividing it up into small triangles, and these are discrete objects. On the right, you have a proof that a graph, a hypercube, cannot be drawn on a plane. And to do that, you find homeomorphic copies of 2 kinds of graphs, which we will go into while doing the project. But right, so each area makes proofs of some essential theorems in the other area very intuitive. And as I said, you have already done MTH 101. Right. We have already done MTH 101, and therefore moving on from that point is not very hard. Is my screen still visible?
Yes.
Okay, cool. Right. Now, the structure of the project will be very flexible and will depend on how many mentees we get and like the level of mathematical maturity and their interests and how much time they have. But the general structure will be that the mentees will be given proofs to read and present. Now, these proofs are going to be very visual proofs, and they may have a lot of gaps in the resources that you are given, and your job will be to fill those gaps before you do your presentation. Starting points can be a topological proof of Kuratowski's theorem and a combinatorial proof of Brouwer's fixed point theorem, and we will go into these while doing the project. But further topics can be picked by the mentees based on their interests. Right. So to summarize, we will have regular meetings and presentations. Mentees will have to give about 3 to 5 hours per week. And this is mostly intended for Y22s and Y21s who want to build mathematical maturity. That's it from my side.
Thank you so much, Nipur. Next up, we have Classify Master. Are the mentors present here?
Yes. So let me share my screen just a minute. I hope my screen is visible.
Yes, it is.
Okay. So yes. So first of all, what is this? Basically, we have the machine learning algorithms which can be used to predict values in two forms. First is continuous. Like, for example, we have age, price, salary, and discrete, such as either yes or no, dog or cat, male or female, etc. So for this, first of all, we have regression, which performs the first task of predicting continuous values, and classification predicts the discrete values. And in my project, we'll be doing the second part, that is the classification part. So we'll be covering the classification algorithms, mostly the well-known ones with both theoretical and practical approach. So what is classification? It's the process of finding a function that helps in dividing the data set into classes based on different parameters. So in classification, we get the computer program to train on the training data set, and based on the training, it categorizes data into different classes. It can be like multi-class or just two classes. We have two types of classifiers, as I said, binary classified. If the classification problem has only two possible outcomes, like yes or no, spam or not spam, etc. And multi-class classifier, if the classification problem has more than two possible outcomes, like types of color, types of animals, types of music, etc. So in classification algorithm, we can have these many type of algorithms, logistic regression, k-nearest neighbors, kernel SVM, naive Bayes, etc. So we plan to cover most of the algorithms. If the time covers, we can cover most of them, or if not, we can at least cover at least 5 of the algorithms, with each of them having a worked out programming code. These are some of the examples of classification algorithms, like to predict spam detection, speech recognition, identification of cancer tumor cells, drug classification, biometric identification, and handwriting recognition. What are the prerequisites? I've kept it open for all the batches. No prior knowledge of machine learning or statistics is required. We plan to cover everything from scratch. Basic Python knowledge is desirable, although we'll help to make you aware of the Python codes and how they're running if you're not aware of the same. Programming work will be mostly done in Python, and we don't have any selection tests for the project. We believe the workload will be very much manageable for you all with your regular academics, and we'll be sharing programming snippets in Python course content. Well, the beginners in Python, those having prior experience in Python, will be at a slight advantage, although not much. There will be 3 to 4 hours of weekly commitment, which I believe is very much doable for you all. And we plan to wrap up the project by mid-June. This is our tentative week-wise plan. First of all, we'll cover the basics. That is, what is machine learning algorithm, Python and statistics basics. Then we're moving to the elementary algorithms like logistic regression. Slowly we will advance to the advanced stage like support vector machine, naive Bayes, decision trees. In week 5, we plan to have the mid evaluation. We'll be giving out the instructions for the same, how it will be done. Later, we'll continue with the advanced part. The 9th week, will be having application with given program examples. And the last week, the 10th week, we'll be having the end term evaluation. Lecture slides, notes, or any other form of resources will be uploading in a master sheet that I plan to share with you all soon. And it will be updated every week with new week-wise content. So as I said before, there will be mid-evaluation and end evaluation. Both of them will be compulsory for the final ratification of the mentee. They are to be done as group projects of 3 to 4. Equal contribution is desired from every mentor. Goes without saying. Although not finalized, every mentee is required to present a programming evaluation notebook for both evaluations based on the application of classification algorithm in daily life. If required, weekly or bi-weekly meetings can be conducted for doubt sessions.
Thank you so much. The next project which is being offered is mathematical trading strategies. The mentors, please take it up from here.
Yeah, thanks. Just a minute. Is my screen visible?
Yes, it is.
Yeah. So welcome to the project, Mathematical Trading Strategies. This is being offered by me and Shivam Pandey. Let's go through the aim of the project first. The aim is basically to learn the basics of trading-related finance, get a good grasp over technical tools and patterns used for formulating trading strategies and mathematics behind them, understanding existing basic algorithmic strategies for profit-making in this domain, develop your own unique trading strategy hypothesis using tools learned during the project, and obviously backtest it. And last, statistically test its significance. Guidelines. There are no prerequisites per se, but we expect some proficiency in Python. Eligibility. This project is basically aimed for Y21s and Y22s. We expect at least 6 hours of weekly commitment, and this should last around 8 weeks. And there is no selection test. I would request Shivam to continue with the weekly.
Okay, so in the first week, we'll first cover some basic probability and statistics concepts that we encounter during trading, and then we'll introduce you to basic, market terms such as risk, reward, trade-off, etc. And we'll continue it for 2 weeks, and then we'll ask you to form some basic strategy. We'll either divide you into groups or make it an individual task. And then we'll move on to week 3, where we'll introduce you to some charting tools and such as TradingView, etc. And we'll give you a gist of technical analysis and things that we use to basically form a strategy, an idea of a strategy or a hypothesis. In week 4, we'll introduce you to basic technical indicators such as moving averages, oscillators, RSI, etc., and how to combine them, how to logically explain their combination, and how to think about them, and how to go over by integrating them into your trading strategy. With week 5, we'll move on to backtesting strategies and running them on live market without using real money, of course. And then we'll also provide you some parameters to judge the strategies such as max drawdown, annualized return, Sharpe ratio, etc., pros and cons of them, and which one should you prioritize for your particular strategy. Then we'll move on to some standard anomalies or strategies. These are strategies which have some expected, which go over the expected profit, such as long-term or short-term reversals and momentum trading, pairs trading, etc. And we'll ask you to combine these and form a new strategy of your own. By going into week 7,
we would like you to incorporate chart and candlestick patterns such as bullish engulfing, bearish engulfing, etc. And we'll provide you some 9 or 10 chart patterns and candlestick patterns and divide them into your groups and provide you the mathematical formula or the initial backing, and then you can go and code it out and integrate it into your initial strategy. And by week 8, we expect everyone to have a robust and working strategy. And by then we'll explain what statistical hypothesis testing is in terms of trading, specifically time series testing. And then we'll determine if your strategy is producing statistically significant profits to be deployed in a market. We are not going to deploy it in a market, just testing it whether it would be feasible, whether it would be a feasible strategy to deploy. And by this, we'll end the project and the presentation. So,
yeah. Thank you, guys. Hope to see you in large numbers.
Thank you so much. Next up, we have knot theory and its applications. Mentor, please take it up from here.
Yeah, hello, just a minute. Is it visible?
Yes, it is visible.
Yeah. Hi guys. So the project that me and Kalash are offering is on the introduction to knot theory and some applications. So what exactly is knot theory? It's actually a subfield of topology. It's a study of knots, which are closed loops or curves in three-dimensional surfaces that are not allowed to intersect themselves. So why exactly are we interested in studying these? That's because actually this field has an interesting history where it was started by a chemist, where he tried to explain atomic structure using these knots. It then evolved through mathematicians playing around with it to what we see today. And around the late 80s, it actually had some interesting implications in physics. This actually ended up unifying mathematics with quantum field theory. And so, since this is such a vast and important topic, we thought we would love to introduce you guys to an intuition behind it and what exactly knot theory is about. So I'll just give a week-wise schedule of what we're planning to do. So given that this is a subfield of topology, the first week we'll introduce you guys to the basics of topology, like what are homomorphisms and isomorphisms, embeddings, and other such ideas. So after that, in week 2, we'll introduce you to the definitions of knots. We'll introduce you to definitions of knots and links. What are some knot moves and some characteristics of knots, such as crossings and unknotting numbers. After this, we'll give you some idea behind what are knot invariants. So, basically, these are certain characteristics of knots which you can use to distinguish between them. After this, we will continue with some of these knot invariants, introducing you to the Jones and Homfly polynomial. Post this, we will tell you about Reidemeister moves and colorability, and this will basically be your introduction to classical knot theory. After this, we will also take a look at braids and braid groups. So this will introduce you to actually some parts of group theory as well. And this will also give you some idea. This will also help you delve deeper into classical knot theory. And finally, we'll have the last week we'll be discussing applications of knot theory, and these are actually very vast, and this will actually be an open assignment where all of you who are participating can find certain applications of your own and discuss, and after we talk about it, you will have to make an assignment or a report on it. So with regards to the project structure, it's quite flexible, and we are in based on the participation and how many people are there, we'll decide how many kind of assignments or reports to keep. We'll have regular discussions every week, probably twice or thrice, and expect around 5 to 6 hours of commitment to the project per week. And apart from that, I don't think there would be any prerequisite knowledge required. We would cover almost anything that you would need to know during the project itself. Thank you.
Thank you so much. Next up, we have our next project, which is data science with R. Are the mentors present here?
Yeah, we are here. Okay, so I think my screen is visible.
Yes, it is visible.
Yeah. So yeah, this is our project, Data Science with R. I, Rohit Jangid, and Siddharth is the mentor for this project. So yeah, aim of this project is to basically teach R and teach data science. So first of all, we'll learn a lot about R, like different concepts of like how to simple variable declaration and a lot of fun stuff in R, like there's RCPP and ggplot and there's web scraping in R. So we'll go over that, and we'll also teach about probability and stuff like that. And so as you can see, there are some things which we will cover. So what is data science and why should we go for data science? Like there's a high demand for data scientists and there's a lot of big challenges regarding big data and stuff. So yeah, and other than that, why we should go for R? Like if you want to go in statistics, R is the thing. And there are a lot of cool things in R which other languages don't offer. And there are a lot of functionalities of R which makes it much more comfortable if you want to do other stuff like machine learning or data science and visualization. So yeah. So what is the prerequisites? The prerequisite is mainly JEE level probability and basic familiarity with coding. So yeah, this project is mainly intended for Y22s, and if there are too many applications, we will have an assessment task. It will mainly have probability questions, and since most of you have done ESC 101, so to test the programming efficiency, we can maybe have programming questions in C and a few brain teasers. So nothing that much. And there's a weekly plan. So yeah, basic introduction to R, plots and visualizations, and web scraping. So this is the fun stuff, web scraping. And like, the R and Python, these all are high level languages. So there's a thing called RCPP where you can integrate C++ codes in R. So we'll teach that. A lot of probability concepts like what are different distributions. If time permits, we will also try to simulate different distributions. Like there's a theorem that we can simulate any distribution using uniform 0-1 draw. So that's pretty interesting. We'll show some examples for it. And now there are advanced visualization techniques like ggplot. It is a really interesting thing. We'll teach you that. And there are Shiny apps. So basically, R provides a feature where you can create interactive web applications for visualization. They are called R Shiny apps. These are slightly tough, but yeah. So we'll do that. And R Markdown. So basically, if you want to create cool code, a cool like LaTeX document, it's similar to that, but not exactly that. R provides a feature to to embed code and make a basically R Markdown. You will learn more about it when you will do the project. So yeah, and we'll have assignments. Yeah, we might have 4 assignments, bi-weekly assignments, or we might even have 1 or 2 group projects. We are not sure about this. We can see how it how the pace of the course is going, how mentees are interacting, and we might change. But yeah, there will be some assignments or a group project, and we'll see. Thank you. So, any questions? I guess no.
Okay, so next up we have forecasting using time series analysis, and I'll be presenting that project. I hope my screen is visible. Can someone confirm?
Yes, it's
Okay, so hello everyone. My name is Lavesh Gupta and I'm one of the mentors. Medha and Shubham are other mentors and they are also present. If you get any doubt during the PPT, you can ask it in the chat and they'll answer it for you. So we are offering a project on time series analysis, and through this presentation, we'll briefing you about the project. So time series analysis basically involves studying the data points which are listed in time order. In this project, we'll be going through the mathematical basics and the statistical tests, as well as we'll study how to perform these tests through Python. Most of you would be familiar with the ML modeling, and we'll learn how we can build models with statistical methods, which are a little bit different than the traditional ML modeling. The objective behind offering this project is to provide exposure to the exciting and untouched field of study. And by the end of this project, you will be proficient in statistical modeling and you will be able to code them up in Python. So regarding the topics that are covered, firstly, we'll have a look at the type of data and we'll do basic analysis and visualization of that data. Then we'll move on to correcting the data that we have and we'll study about handling the missing data and outliers in the data. Next up, we'll study the characteristic and component of time series, which is a very important part. We'll study about trends, seasonality, cyclic variations, and residuals. We'll also see techniques like smoothing and decomposition. Next up, we'll move to the most important part of the project, which is the time series models, and we'll explore each models one by one. And this is not all. We have included applied mini projects at the end, and for those we have stock market forecasting and a business case study as our mini project. More information on these projects will be provided later in the later course of the project. And since this project is about time, so we'll talk about the timeline and commitment. So the project is of 8 weeks and we expect a commitment of 6 to 7 hours per week. And most of these hours would be for attending the online meets and submitting the assignments and reading the Jupyter notebooks that we offer to you. And the timeline, although we have a fixed timeline at the start, we can vary according to the comfort of the different topics that are covered. And moving on to the prerequisites, there are very basic prerequisites like you should be able to have, like you should have basic knowledge of Python and J level statistics. One important thing is that we are aiming to have active participations, like the freeloaders, they won't be entertained. So if the participation is active, you'll get ratification. The intended audience for this project is Y22 and Y21. And we are expecting around 30 to 40 mentors and mentees, and we'll take more mentees on a case by case basis. So these are the mentors for the project. Myself, Lavesh Gupta, Medha is also here, and Shivam is another mentor. If you have any questions, you can ask them here, or you can also DM it to us on Discord, and we'll happily answer it for you. Thank you. Okay, so next up we have Introduction to Machine and Deep Learning.
Yeah, I'll just share my screen right now. So I guess my screen is visible to you guys. So this project is called the Introduction to Machine and Deep Learning. And this is being mentored by Akash Mishra, Arindam Bora, and myself, Anvesh. So we know that the generative models have taken the internet by storm. You have GPT and Dolly, which is basically the hot topic right now. And machine learning is surely one of the most coming up fields in the future. So this course will basically be a short introduction to writing such machine learning models. So in this course, we will be going through the mathematics behind some of the popular machine learning and deep learning algorithms. And we will also be implementing such algorithms in Python from scratch using some basic libraries. And regarding the deep learning libraries, we will be using PyTorch to build our own deep learning models. And we will be going through the process of generating, pre-processing, and visualization of data. And this project will end with a hands-on applied project, which will consist of everything which we have learned till now. So we will now go through the week-wise plan of the project. So this is a tentative timeline, and it will start with the mentees learning about data generation, data pre-processing, and using some libraries to visualize the data using graphs and plots. Then it will be followed by some classification and regression algorithms. Week 2 will consist of some algorithms like linear regression and logistic regression. Week 3 will have classification algorithms like KNN, naive Bayes, and decision tree. And again, we will be going through the mathematics and the code from scratch of all these algorithms. Then we will be covering the unsupervised machine learning algorithms, clustering and dimensionality reduction. Before the midterm evaluation, we will be covering the basics of PyTorch, which is a popular tool to build your own deep learning models. Hopefully by week 5, we will be having a midterm evaluation. After that, we will be going through the deep learning and neural networks and learn about gradient descent. Then we will be learning about hyperparameters and how we can tune them to actually get the best model. Then the last 2 weeks will be covering CNNs, which is basically used in computer vision. We will be implementing CNN using Keras, PyTorch, or TensorFlow. And hopefully by the end of the project, we will be doing a transfer learning and a hands-on project. So coming to the logistics of the course, so we expect the mentees to dedicate about 8 hours of their weekly time to the project. And the project will be about 10 to 12 weeks. The mentees will be given weekly coding assignments, which will contain Kaggle data sets or some assignments, coding assignments. So both Y21 and Y22 are the intended audience for this project. Regarding the prereqs, we want you guys to be familiar with Python and libraries like NumPy and Pandas. It will be helpful to know that NumPy arrays and Pandas, data frames and their manipulation, like resizing, concatenating, arithmetic operations, broadcasting, etc. Basic linear algebra and differentiation are prerequisites that most of us are familiar with, hopefully. So I guess that's it from my side. Feel free to contact us if you have any doubts. These are the Discord handles, which you can see on the screen. So if you have any doubts, you can ping us anytime and we are free to clear them. So yeah, thank you.
Thank you so much. The next project which is being offered is mathematical predictor using machine learning. Are the mentors present?
Yeah, I'm present. Is my screen visible?
Yes, it is.
Hello everyone, I am Siddharth and I will be mentoring the project Mathematical Predictor using machine learning. I will be co-mentoring this project with Rudransh. Coming to overview of the project, our project will be based on the mathematics that is used in various aspects such as linear regression, gradient descent. We will then move on to regularization and optimization techniques generally used. In the later part of the project, we will be studying about ensembling learning, Bayesian methods, and dimensional reduction methods.
I would like to focus on the fact that our project will be based on understanding the equations rather than implementation of a machine learning model. These are the topics which we aim to cover in our project. We will be teaching first the basics of the machine learning and then moving on to the mathematical aspects behind them. Coming to the logistics of the project, there are no prerequisites as we will be teaching you the basic machine learning concepts before moving on to the mathematical aspects. The expected duration is about 2.5 months and we expect a weekly commitment of around 4 to 5 hours. And the intended audience for us is Y21 and Y22 both. Thank you. Feel free to contact me or Rudransh for any queries.
Thank you so much. We'll move on to the next project, which is image processing and computer vision. Mentors, kindly take it up from here. Are the mentors present? So we'll be moving on to the next project, which is You Only Look Once. Mentors, are they present? I guess there is some network issue. So for now, we'll move to the next project, which is PhysiLearn, learning physics through neural networks.
Yeah, hi. Am I audible?
Yes, Sagar.
Yeah. Okay, so I am Sogat Kanadia. I'll be a mentor for this project. You only look once. So basically, I think you all might have seen this famous dilemma. Like, what this is an ethic game based on self driving. Like, should it hit the barricade or should it kill the dogs? So, we are not going to take a course on this ethics thingy, and we are just going to take a normal project on CNN discussing the technical aspect. So, we take the example of self-driving cars. In this, we can clearly see that what a self-driving car wants to do is detect its obstacles. So we try to make some bounding boxes so that we can identify what kind of objects we want to avoid. So our project is based on this. What I expect is you should have some prerequisite knowledge of linear algebra. If you have done it in MTH, that's fine. And basic class 12 linear algebra would also work. And some prior exposure to Python, like no advanced stuff, just basic arrays, for loop, and all. The logistics will be like, I want 6 to 8 hours per week for this project. And the plan is of 5 weeks content and 3 weeks for the implementation portion. And we will try to give assignments, and we expect them to be completed before the deadlines, and we'll try to host regular meetings as per the requirements. Okay, so this is our timeline. In the week 1, we will try to revise some of the topics that we are asking as prerequisites, like Python, NumPy, Panda, the basic libraries in Python. And we'll go through what deep learning is, what neural networks are, what are activation functions, and we'll just give a brief overview of what deep learning is. In the next week, we'll go over CNNs, convolutional neural networks. We'll talk about what are they, how are they implemented, what are its features, and what is stride, what is pooling. We'll discuss many types of pooling, and we'll try to look at some famous architectures in this too. Next, we'll go over how CNNs will be implemented in Python, and how we will use the libraries like TensorFlow for building the layers, and try to discuss some implementation using CNNs, which we'll ask in the midterm eval too. Next, we'll talk about some applications of CNNs like object detection, image segmentation, like the application which is used in cancer detection. And we'll talk about some famous architectures, like which you can see here. We have InceptionNet. It looks very complex, but it is just a combination of various convolutions, strides, pooling, and fully connected layers. Then we'll talk about YOLO. We'll talk about transfer learning, which is purely dependent on whether we have that much time. And we'll try to talk about transfer learning too. Then we'll go over YOLO algorithm. This we'll do in depth, and we'll talk about the various aspects regarding this. And the final end eval will be based on image detection using YOLO algorithm. We are not discussing what it will be about. We'll go over that when we come to the end of the project. And in mid eval, we'll try to do a basic classification of handwritten digit recognition based on the MNIST dataset. That will be all from my side. These are the project mentors, Rohan Virmani, Sri Lakshmi, and myself, Sogat Kanaja. Thank you.
Thank you so much. Next up, we have our next project, which would be networking of nodes. Are the mentors present here? If any other mentor would like to present, they can go ahead while the other mentors join the meet.
Can we go ahead and present cryptographic applications of number theory and abstract algebra?
Yes, Shashank, you can go ahead.
Okay, thank you. Is my screen visible?
Yes, please go ahead.
Okay. So I, along with Aditya and Mir, would be offering this project cryptographic applications of number theory and abstract algebra. So the syllabus basically would be that we'll start with some basics of number theory that would cover Euclid's algorithm, Bezoart's identity, Fermat's little theorem, Euler-Thorsen function, Chinese remainder theorem, and Diophantine equations. And if the time permits, we might extend to combinatorial number theory. Then we would start with abstract algebra that would cover group theory, rings, fields, finite fields, and algebraic closure of fields and their applications. Finally, we would be moving to the above applications in cryptography after we would be covering the basics. What the main motive of the project is that we would cover key exchange algorithms like RSA. Then we'll culminate with the most used encryption algorithm AES, Advanced Encryption Standard. Quality over quantity is that what we are aiming for, weaving into the complexities leading to something that we can appreciate in general. So what was the weak-wide distribution? The weak-wide distribution would be something like this, that the overall project can be broadly divided into three parts. What we'll be mainly focusing in the beginning would be number theory and its concepts that would be ranging from first week to the third week. In the further follow-up week, we'll be covering the abstract algebra and group theory part. That will be the main focus and base for developing the uses of cryptographic applications. And in the further last week, we would cover the cryptographic applications and some cool algorithms that are used in the modern world, which would be the final part of the project. Some broad aspects, what we'll be covering in first week to third week, that would be an introduction to number theory as discussed before in the syllabus, that what would be things that we would cover. And we should find its uses in probability testing and public key cryptography, which shall be covered in further weeks. Euler-Thorsen function and Chinese remainder theorem shall be discussed to provide functionality for modular computation. That is very useful when we're dealing with large numbers. If time permits, we would also cover the basics of algebraic number theory that aligns with abstract algebra, combinatorial number theory, where we would include Cauchy-Davenport theorems and van der Waals theorems. We would also see some relevant and interesting problems on this. And if time permits, even after covering all of this, we could even see some parts of divisibility and density in number theory. A week shall be committed to discuss brainstorming problems and assignment questions. And I think they are going to be very interesting. Moving to the next part of the project, that would basically be more oriented towards the group theory. So we will build a motivation that why we should deal with this. First, we will provide introduction to groups, how their abstractness are, what are their applications, and their build-up would be done as it would be required to learn the algorithms covered in cryptography. Following that, an introduction to rings and fields would be done, and their robustness would be discussed, and that would be required in key exchange algorithms and hashing. Furthermore, a thorough discussion of a range of problems would be covered to strengthen the concepts and broaden the approachability to the problems. When we are done with the establishment of number theory and abstract algebra, in the follow-up week, we would come with the main motive, that is to discuss the cryptographic applications. First, it will start with the most used encryption algorithm in today's world, that is advanced encryption standard, and we would do a thorough analysis of this. Then we'll have a deep dive into the usage of taught concepts and try to mount an attack on this algorithm. After learning the importance of key exchange algorithm using AES, we move to the most popular algorithm, that is RSA. Following this, we will have a venture into the key generation mechanisms and some specific details of RSA that would use the order of groups and smooth primes. So, what are the logistics of the project? Logistics of the project include that we'll have bi-weekly meets, and that would be of 1 hour each. Depending upon the mentors and mentees, the meet can be online or offline. Each week, we will first teach the topics, followed by the discussions of assignments and questions. The assignments will also be bi-weekly. They will consist of fun puzzles, which will require the knowledge of the topics covered during the project. The weekly workload for the project can be approximated for about 7 to 8 hours, and the intended number of mentees will be approximately 30. And no prerequisites are required, only an enthusiasm for solving relevant and interesting problems are needed. That's it. And the intended audience will be Y22 as well as Y21. Moving to the evaluation criteria, the weekly assignments given during the course of the project are for the understanding of the students. This will help mentees to know that how much they have learned and grasped so much far. These will be discussed but will not be considered as an evaluation criteria. What would be the evaluation criteria will be that each mentee will have to submit a project report for the midterm and the end term evaluation, stating what all they learned during the course of the project and also highlight some of the examples of the concept that they learned. And these are the contact details of all the mentors, Aditya, Mir, and me. So if there is any query or concern, you can contact on any of this.
Thank you so much. Next up, we have mathematical foundations of computer graphics, rendering, and lighting. Mentors, please take it up.
Okay, am I audible?
Yes, Professor.
Okay, I'm sharing my screen now. Please confirm if my screen is visible.
Yes, it is visible.
Okay, so hello everyone. This is the project Mathematical Foundations of Computer Graphics. So in this project, basically, what we'll be doing is looking at some of the maths behind how graphics are actually rendered on your computer screen. How any graphics or any element on your screen which you see is actually being rendered. How every pixel gets its color on the screen, right? So uh, when we talk about computer graphics, there are like multiple ways to go about this, and one of the most popular ways in which we basically do things is called ray tracing. And in that, what we have is a light source typically, which shoots light rays, and it hits different objects, which in turn hit other objects, which will create shadows, and ultimately it will hit the eye, or like let's say camera in this case, because we have a screen to go through. So after the lights have hit the rays, we'll have an image generated on the screen, right? So the only problem here is there is no actual sphere in the scene. Like whatever we are seeing isn't actually there. We have to simulate it basically. So all of this is in a way a mathematical construct which we see, or which we are able to see only because we do some calculations behind the scenes and allot a specific color to each pixel on your screen, right? So we'll be diving deep into the concepts which we'll use to find out how we can simulate this, how we can make it as realistic as we can, can we make it, how we can like simulate the real physics behind the all the light calculations which are going through, right? So to get into the actual content of the project, in the first week we'll basically look at why do we really need to use these type of calculations for this, and what are the applications in which we can use this.
And then we'll look at the rendering equation. So a rendering equation is basically a equation which tells you that at any given point in a space, what will be the intensity of the light and the color of the light, which our eyes will perceive depending on what our light is it's receiving from other sources and what is the surface properties, right? And this rendering equation can be varied based on what type of effect you want. If you want a realistic image, we'll have a different rendering equation, and if you want a cartoonish look like the one Disney uses, maybe it will have a different rendering equation. So we'll take a look at that, and alongside the theory of the equations, we'll try to set up a project structure. So basically, the objective of the project is to be able to make computer graphics, right? So we'll need a pipeline where we can put in code or do mathematical calculations, and it gives us an output of a computer graphics, right? So we'll try to set up those project structure on the basis of which following weeks we will be able to render computer graphics, right? So in week 2, we'll be doing the actual ray tracing algorithm, and in that we'll be implementing the material properties of different objects, like what is the color of a material, is it refractive, is it reflective, is it metallic, so and in which direction is the light coming from, shadows. So all of these properties of the material, how can we simulate that into our ray trace, right? In the following week, we will cover some. Although it's not directly related to realistic rendering, but it has a really cool notion that you can use math to generate cool, realistic looking graphics, right? So for that, which we basically call as procedural generation. For that, we'll use random numbers. We'll take a look at how we can generate random, pseudo random numbers, because we can't really generate truly random numbers, and how we can use that to generate noise and add octaves on that. And using that, we can generate height maps or terrain or other realistic looking graphics. In the following week, we will like improve our ray tracer to add more effects, such as adding manual lights into our scene and simulating certain effects such as fog or other volumetrics through probabilistic calculations. In the following week, the week 5 we'll be keeping as buffer time if the content of week 1 through 4 is a bit intensive, and it's possible that you might not have been able to catch up. So we'll keep week 5 as a buffer time or doubt solving time, and it will also act as a mid eval thing where we'll see if people are able to catch up on the assignments which we'll be giving. And for those people who are interested, we will maybe try to simulate 3D fractal in the ray tracer which we have built. A week following that, so basically week 6 and week 7 would be certain topics which are not directly related to ray tracing, but there are some miscellaneous topics which need certain mathematical foundations which are applicable in computer graphics. So we will try to cover that. And that week 6 is basically curves, splines, and tangents. So in generating 3D scenes or computer graphics, these play very important role. So till now we have been generating like primitive shapes like spheres or cubes or cuboids. But what if we need to generate a mesh or a object or shape which is of random configuration, or it has some random contour? So we can simulate that using curves, but those curves need to be smooth, or they need to have continuity in them. How do we achieve that using maths? How do we ensure there's continuity in the splines of the curves which we are generating? Um, so week 6 will basically cover that, and the week following that will be um, generating mesh from continuous objects. So suppose if we have a sphere in our scene which we can just define through a radius and a center, right? So we have a center, we have a radius, so which basically defines the surface of a sphere. But when we store the information into a 3D model, let's say, we need to have a mesh which is composed only of triangles or quads. So how do we approximate those curved surfaces through meshes is what we'll cover in this week. And the main algorithm for doing this, which we'll be covering, is Delaunay triangulations. Um, so this will be the content of the project, and the logistics would be the workload is going to be around 9 to 10 hours. The duration is 8 weeks, and the evaluations would be, we'll be giving you weekly assignments, and week 5, as I said, would be kind of a mid-eval thing, and in the end we'll have an end evaluation, which you will be building a scene of your own using your own ray tracing. So the expected audience is Y21s and Y22s if you have some basic C++ knowledge, as C++ is a language we'll be using to build our ray tracer. So this was all about our project. Thank you, and feel free to discuss any doubts if you have on this. Thank you.
Thank you so much, Prakhar. Next up, we have image processing and computer vision. Please take it up.
Hello, am I audible?
Yes, you're audible.
Yeah. Yeah, so hello everyone, I am Subhajit Mishra. Me along with Akshat Agarwal are offering a project on image processing and computer vision. So basically, let me start with the what all topics we will be covering during the project. So we will start with probability and statistics. We would brief upon various concepts of probability and statistics which are highly essential for image processing and computer vision. We will just look upon the various spatial distributions and their covariances and correlations. Like there is nothing, we will not go much deep into various equations. We will just dive on surface level which are required for the project. Then we will come to the image domain. Like basically, probability and statistics is a highly essential field for signal processing, and image is also signal. So we will then proceed completely into the image signals. We will start with teaching various parameters in an image, and then how we use those parameters to amplify or to use the various important features of image as per our requirement. So we will learn about sampling and quantization, image enhancement, edge detection, image segmentation, and image denoising in a broad sense. We will go into much details in each topic wherever it is required. Now coming to the week-wise plan, we will start our week 1 with probability and statistics and brief overview about the various aspects of the project. So we will have an assignment in the end of every week. In the week 2, we will learn about the various distributions. So basically the first 1.5 weeks will be on probability, and starting from the second week, we will delve into the image domain. So from week 2, we will have we will start image processing and have assignments on that. In the week 3, we will learn about maximum likelihood and testing hypothesis, and then we will learn from week 4, we will know about the various image processing algorithms. We will learn the various algorithms, how these algorithms are used to process an image, what are the usefulness and demerits of using any algorithm. Then we will code each algorithm, and then we will also know how various libraries like computer vision, CV2 libraries and all, they have listed down various algorithms and how to use them while running a big program. And like we will first code each algorithm from scratch, and then we will know how to use the various library functions. And finally, in the week 6, we will have a project on computer vision or machine learning, where like basically our motto is that computer vision is done by various authorities and various bodies do computer vision, but data pre-processing or image processing in the case of computer vision is a very important aspect which many people neglect. And we will know how processing the image before computer vision can give very really wonderful results. And that will be the main motto of doing the project or doing the entire week, 7 weeks of work. Then we will, like in the week 7 will be simply recommendations about how what are the future endeavors in this field and how you can proceed further. Like this is a short duration, so we can only cover limited things. So we will then proceed on. In week 7, we will basically learn about what are the various fields that have opened by learning these concepts. We will have assignments at the end of every week. Like there will be coding assignments. Those will be coding assignments. Some assignments will be on processing images. Some assignments will be on coding the algorithms that we have learned during the learning lecture, during the lecture hours, or during the meets that we will conduct. We will basically code the various algorithms and compare it with the other algorithms already available. We will have a midterm where which will be a combination of 3 assignments, and we will have an interim evaluation which will be the project. There will be an assignment on the algorithms, and then we will have a project on computer vision. And the project will basically we will basically use image processing first, and then we will use machine learning to find the required thing. So this will be the entire timeline and work of the project. There is no there is basically no batch criteria or eligibility criteria for entering into the project. Anyone from any batch can enter into the project. The only requirement is enthusiasm. The other requirement is that knowledge about, at least some decent knowledge about Python, because the entire project will be based on Python. Like the assignments and the machine learning projects and all, everything will be done on Python. So Python and Jupyter Notebook, it's fine if you don't know Jupyter Notebook. Python is a must. And if you have some knowledge like ESC 101 or ESC 111, and like some computation knowledge on how to code after knowing an algorithm, then it's an edge. Yeah, it's fine. Knowing Python is an essential factor, because in the short duration, teaching Python or learning Python by yourself might be a bit challenging. Yeah, so that's all in our project. Thank you.
Thank you so much. Next up, we have networking of nodes. Are the mentors present?
Yes.
Kindly take it up from here.
Am I audible clearly?
Yes.
Okay. So, uh, our project is of networking of nodes. This project area is graph theory, trees, and algorithms like that. So, graph is basically data structure in computer algorithms. So, next slide. So, basically, we will cover DFS, BFS, data cycle in graphs. DFS, BFS is mainly traversal algorithms. DFS depth for search, BFS breadth for search. These are mainly algorithms which have most of the questions of the graphs. And then we have the Disaster algorithm and Bell-Manford algorithm. So which are for single source to multiple source and multiple source to multiple source, followed by flood version algorithm. And flood version algorithm is for all pairs shortest paths. And then Kruskal and Prim's algorithm for minimum spanning tree also. And then we have Kosaraj's algorithm, Dargel's algorithm, which is related to bridge, and then some applications related to bridge, finding artificial points. Then topological sorts, which are used for linear ordering of some special kind. Then we have strongly connected components, and they are similar topics. And then red black trees, up to some extent only theory part. And we will also cover some algo parts like advanced algorithms like PSU and try. And also linked list you might have also learned in ESC 101 or ESC 112. Then binary search and sorting up to some extent. And then we have this week-wise plan where those all topics are sorted in this week-wise plan, like basic properties of graphs, basic of data structures, DFS, BFS, sorting, and all this. And then this week 5 to 8 plan, this general questions and important. Initially, we will be making some introduction to algorithms, then some question implementation part, then again theory part, then again questioning part. So next slide. So there will be three major contests in this whole project, which will hold the most part of the evaluation, uh, which will be around in week 3, 6, and 8. And discussions will also occur for this contest. Also, there are marks for attendance and exercises. That's nearly 10%, but it will also occur. 3 lectures, and also recording will be provided for the lectures uh, for those who can't attend the session on time. Also, there will be nearly a weekly commitment needed, 6 hours per week. Then next, prerequisites should be somewhat familiar with C and C++, or and ASC 101, 111, 112, whatever. And number of students can be arbitrary. And that's all. Thank you.
Thank you so much. Next up, we have PhysiLearn, learning physics through neural networks. Are the mentors present?
Yes, am I audible?
Yes, you are audible.
So yeah, here we are presenting. Om Shivastav, Imad, Ayush.
Yeah.
So what is PIN? So PNNs are a type of neural networks that can be used to solve differential equation. Like you will get to see in your engineering that there's a lot of in engineering we solve a lot of differential equations through numerical methods or through actual method to solve that. So why PNN? Why we want to use neural? Here we want to use artificial neural networks, machine learning, to solve these problems. So here we can see that PNN have shown to be more efficient and accurate than our traditional methods. So you will get to see the importance of differential equations. So differential equations are across all over the engineering, physics, and material sciences. So what are the importance? Because why are they important? Because they allow us to make predictions about the future event, or at any specific or at any other space in at any other point in space. Traditionally, differential equation has been solved using numerical methods, as you guys can see this in ESC 20. Hello. Yeah. So traditionally, differential equations have been solved using numerical method, such as finite differences or finite element method, which will be taught in ESC 208 course. But these methods work by discretizing the problem and domain into a grid of points, like we are dividing, like we have a small difference like 0.01, 0.001. So the smaller the difference, the better our approximation gets. While this method can be effective, but they have some limitations. So let's look what introduction to PIN. What PIN is. So as I have already told that PIN are neural network which will learn relationships between input and output. What's the use of neural network? Like it learns a relationship between an input. We will give an input and train it with a given output, certain output. So what are we going to give it as input? Like the position and the time. This okay, and then we get the output as demanding, like what the solution of the differential equation, like what we get the solution, like the points and the velocity, kind of, we could say. So this allows the network to predict the behavior of the particular system. Like I have a system
I'm observing it, like I've given some x velocity, so it's behaving in certain behavior. So x will be my the x velocity will v velocity will be my input, and that certain behavior will be my will be my output. So I will be training on these input output. So this will learn, like it's like you will do and learn, like practicing kind of what here you want to make a comment?
So we'll model the physical system on the basis of the prediction between the value of input and output. So like any system on the like, if it is related to stress strain or any sort of like physical inferences, so we will like model the system. You can say like, for example, say harmonic oscillation or something sort of this.
So as I've already said, PINNs have several advantages over traditional methods, including the ability to handle incomplete or noisy data. That's kind of thing you can go. So what is the architecture of PNN? So it looks something like this. Like we have given as input x and y, the position and the time. So here is a neural network. So we get a something variable like what we want to it's kind of, you could say, what we want to know, like it's a differential equation to solve something, and then what the differential equation like PD, what is our given differential equation. So we want to find the solution. We want to find the solution to the differential equation. It's kind of like that. So for the PD, for the network of PD, it will vary from various differential equations. So you will get to see much more in the as you can ask from us on DM. Yeah. So this is the architecture of PINN. It consists of input layer, output layer, and several hidden layers. And there is also a physics informal layer, which is a kind of like differential equation. The input layer receives the input parameters. Then the hidden layer perform the nonlinear transformation that are hidden, that we don't know, like how to fit our model. It's just fitting the model to that particular differential equation. Then the physics informed layer is the differential equation we put constraint on. So what are the applications? So application of PIN are quite wide, like solving differential equation, fluid dynamics, and turbulent modeling. This can help. This can help us in fluid dynamics. Like we don't know, Navier-Stokes theorem. Sometimes it gets quite difficult to solve these without if we didn't have good boundary conditions. So here PNN can help us in modeling and predicting the behavior of material under stress, like stress strain kind of thing, like Om already said. Designing and optimizing complex mechanical system, it can help in, like for the dynamic system we have differential equation, but solving it gets quite more intense, and it's sometimes it's not quite solvable in a traditional way. So PNN also helps in such a in these matters, like rest all, like reaction coefficient, like such a diffusion coefficient in a reaction diffusion equation. Like these all the application. So what will be the learning objective? So how the physics informed neural networks works. So this is the basic thing you will be learning in this project. Recognize the advantage and limitations of PINN compared to traditional methods. Here we'll be presenting like when we won't be when will it limit the like there is a point that we can't use PINN, like we didn't get lot of for the PINN we required a lot of data, but if we didn't get that much, we get very small sample of data, we won't be able to train our model well. Then we will explain the architecture and training process is kind of, and then identify real world application and apply the PNN model to that particular differential equation. and appreciate the potential impact of PNN on solving complex physical problems. Like for any, if you want for any physical problem, it is directly related with the differential equation and solving it with a PIN layer from through PINN. So we get to see a lot of we can conclude a lot of things from this. So this project will run for 8 weeks. We are going to recruit around 30 mentees. Hope to see you in large numbers. It can vary depending on the participation from the mentees. Yeah, yes, we will going to have a recruitment test. It is on basics of Python and in linear algebra that maybe in your JE level will suffice. The project will cover theory as well as application of neural networks on physical system. The time commitment, it's quite much, but yeah, we are expecting that mentee should spend 8 to 10 hours per week. So here is the week timeline for week. So first, in the first week, we will begin with Python libraries. In the second week, we will get into the deep learning, like what deep learning is, basic regression, and the gradient descent kind of thing. And then we get there's a lot much more things are left in deep learning, which you need to be know, like activation function, biases, errors, neural networks. So we will cover this in week 3. And then up to week 3, we are going to teach you neural networks from scratch. So now in the week 4, we are going to teach you Torch, introduction to Torch. Because with the help of Torch, we can implement neural networks very easily. And then in the 5th week, we are going to teach you PINN, what physics informed neural network, what PINN actually is. And then its implementation on harmonic oscillator. And there is a final week evaluation of heat equation. Like we will giving you heat equation, and you need to train your model on heat equation. So these are the assignments. Like first assignment will be from Python libraries, and the second assignment on ML regression, then neural networks and linear algebra. It's a theoretical one. And the Torch, like we will give you a half code, like incomplete code of on collab file, and you need to complete it. And then differential equation and mathematics for physics, like it's a theoretical one. And then the final evaluation of heat equation. Last but not the least. So we also have one more thing. If you do everything on time, or just if you do everything ahead of time, then you can, if you are, and you also want to continue with neural networks. So we have something, the self-driving cars. So here is a link. So we will try to implement this. This is our neural network model, and these are the simulation which it works on. So like after a lot of generations, like it getting better, you will get to see how the neural networks get trained and get better over time. So in the end, now you could see like it's not crashing. So if you are interested after the project, we can also work on this. So thank you. Here are the contact details of us. Thank you.
Yeah, so thank you everyone. This is the end of the presentation, and the forms are already out. You can fill up the forms till 10th April midnight. You can fill up to 10 preferences, but at least 3 preferences are required, and some mentors could conduct a selection test for which you are interested. So please fill up the forms carefully. And yeah, this is the end. Thank you for joining.